This talk is called Gravity and Black Holes. Introduction. Black holes play an important part in the current paradigm in astronomy, astrophysics and gravitational physics, and so it would appear naive to question their existence, especially as several research groups already claim to have obtained observational evidence for them. Indeed, even if some of this evidence turns out to have origins other than from black holes, it is still impossible to deny that black holes could exist, since, from a philosophical point of view, they can be regarded as non-falsifiable. According to received opinion, an astronomical object such as a very compact star becomes a black hole if its mass is contained within a so-called event horizon. Space-time is then curved so much that nothing can escape, not even light. Furthermore, at the centre of the black hole is a point singularity where the laws of physics break down. Most scientists firmly believe that such entities exist in the universe. But in this talk I want to suggest a model for a point mass that does not require the presence of an event horizon or a point singularity, and where the gravitational attractive force between masses does not diverge to infinity. Hopefully, scientists will wish to test my model in conjunction with, for instance, the intriguing behavior of stars near the center of our own galaxy, as well as the images of galactic centers published by the Event Horizon Telescope team. Background theory. Black holes were given a strong theoretical foundation many decades ago using Albert Einstein's theory of general relativity applied to the problem of finding the gravitational field due to the curvature of spacetime near a point mass. The starting point is to write a metric line element for the four-dimensional spacetime around a point mass, as in equation 1. The quantities A, B and C are radially dependent functions describing the curvature of time, radial and angular metric coefficients respectively. This is the most general way of expressing spherical spatial symmetry around a point mass. Almost all contemporary treatments replace C in the metric with r squared, in which case the solution for the spacetime curvature is found to be given by the well-known result A equals 1 over B equals 1 minus alpha over r, where alpha is an integration constant. The idea of a black hole now becomes apparent, since the quantity A equals 1 minus alpha over r changes sign if r passes through alpha, and the inverse function B becomes infinite as well as changing sign at r equals alpha. A hypothetical sphere of radius alpha is thus imagined centered on the point mass at the coordinate origin r equals 0, called the event horizon. The radius of this sphere is usually called the Schwarzschild radius or gravitational radius, and the coordinates used when c equals r squared are commonly called Schwarzschild coordinates. In his original solution, Schwarzschild realized that the solution becomes negative if r goes to less than alpha, but he defined an auxiliary radial coordinate to prevent this happening. He therefore did not actually predict black holes himself, even though current popular science often suggests he did. One should note that replacing the more general functional C in the metric with r squared enables a solution to be obtained, but it is tantamount to defining a new radial coordinate. Thus, with C equals r squared, r is then not rigorously the same as the true radial distance from the origin. How the current paradigm subsequently came about is roughly as follows. Soon after Schwarzschild tragically died at an early age, both Droste and Weil published a different variant of the solution, essentially in which they avoided the discontinuity by limiting the range of r to alpha less than r less than infinity. Subsequently, Hilbert extended Droste and Weil's solution into the range r less than alpha, that is, into the region where the functions a and b become negative. Hilbert's argument for extending the solution was essentially that GR is conceived as a generally covariant theory, meaning that a change of coordinates should not alter the physics of the situation. This is the currently accepted solution and reasoning. Comparison with Newton's classical law. GR is essentially an abstract geometrical description of how space-time is curved by stress energy, such as mass. In order to obtain correspondence between this and experimental observation, we can make use of Newton's law of gravity. For this purpose, consider a test particle falling from rest a long way from the point mass m, along a radial direction towards m. The geodesic equation for r, which can be obtained from the metric in a standard way using the calculus of variations, provides the following expression for the radial equation of motion, in equation 3. This is then compared with Newton's law in what is called a weak field approximation, that is, in the regime where Newton's law applies. Indeed, Newton's law does not describe certain aspects of gravity correctly, for example, the anomalous perihelion rotation of the planet Mercury and the bending of starlight passing close to the Sun. However, Newton's law is very accurate for all ordinary cases of gravitation that we encounter, such as planetary motion and free fall. The weak field approximation actually requires 3 approximations. Firstly, the particle velocity r dot is regarded as negligible compared to the speed of light c, such that the term in r dot squared can be neglected compared to the first term on the right-hand side of equation 3. Secondly, the proper and coordinate times are regarded as equal and the same as time in Newton's law. That is, we write t dot equals 1. And thirdly, space is not curved, so b is set equal to unity in the first term on the right-hand side of equation 3. The proper acceleration is then given by r double dot equals minus 1/2 a dashed c squared, and equating this to Newtonian acceleration minus gm over r squared, we have agreement between the two approaches with alpha equals 2gm over c squared. Alternative proposal. The weak field approximation outlined above is unsatisfactory in my opinion, and it is better to proceed as follows. What primarily characterizes Newtonian behavior is that there is no spatial curvature. That is, his inverse square law of gravitation pertains strictly to a flat or Euclidean space. Thus, to obtain the correct correspondence between Newton's law and the equation of motion from the calculus of variations, we need primarily to set the metric coefficient for spatial curvature b equal to unity. Doing this in equation 3, we obtain r double dot equals minus 1/2 a dashed c squared t dot squared. Next, we do not set t dot equals 1, but rearrange the metric to write t dot squared equals 1 plus r dot squared divided by a c squared. Finally giving equation 4 r double dot equals minus a dashed over 2a times c squared plus r dot squared. This now describes and represents Newtonian free-fall motion in the 4-dimensional space-time geometry of GR more accurately than the previous weak field approximation. Solving this differential equation by using the asymptotic condition r dot equals 0 for a equals 1, we obtain a equals 1 plus r dot squared over c squared all to the power minus 1. And if we now set r dot equal to the Newtonian velocity of free fall, the square root of 2gm over r, we obtain a of r equals 1 plus alpha over r to the minus 1, which gives a goes to 1 for r to infinity, and a goes to 0 for r to 0, and alpha equals 2gm over c squared is the same quantity as before. This expression for a can be regarded as resulting from the postulate that Newtonian gravity is determined purely by the curvature of time in a Lorentzian four-dimensional spacetime. The corollary to this is that deviations from Newtonian gravity, such as the anomalous perihelion rotation of the planet Mercury and the bending of starlight past the Sun, are caused by the additional effect of spatial curvature. The solution A equals 1 plus alpha over r to the minus 1, with B equals 1, does not satisfy Einstein's GR field equations exactly, because it was derived as an approximation to represent the conditions under which Newton's law applies. Postulating that this part of the solution remains valid under all circumstances as the contribution due to time curvature, we can then use general relativity to obtain the contribution due to space curvature, which is then given by B equals 1 over A equals 1 plus alpha over r. In the metric, the radial coordinate used in the black hole solution with capital C equals r squared is not identical to the true radial coordinate distance r. So if we now call that radial coordinate r with a bar over it, then we may write 1 minus alpha over r bar equals 1 plus alpha over r all to the minus 1. Rearranging this expression gives the simple linear relationship between r bar and r. R bar equals r plus alpha. Thus, A and B remain regular for all values of the true radial coordinate distance r from infinity to naught. So although A of r bar and B of r bar change sign at r bar equals alpha, this does not represent a discontinuity in spacetime, since from equation 8 the range of r bar is restricted to infinity greater than r bar greater than alpha. Thus, using this interpretation, the concept of a black hole with an event horizon is seen to be false, and the extension made by Hilbert to r bar less than alpha is invalid. New law of gravitational attraction. Using the metric, equation 3 may be rewritten as r double dot equals minus a dashed over 2ab times c squared minus a dashed over 2a plus b dashed over 2b, all multiplied by r dot squared. Substituting the proposed GR solution, a equals 1 over b equals 1 plus alpha over r to the minus 1 into this, we obtain the complete free fall behavior r double dot equals minus 1 half c squared a dashed equals minus 1 half c squared alpha over r plus alpha all squared as equation 9. This expression shows classical Newtonian behavior for r very much greater than alpha, but deviates from inverse square law behavior for r of the order of alpha. That is, the acceleration increases as gm over r plus 2gm over c squared, all squared. But for r to 0, it reaches a constant value of c to the power 4 over 4gm, rather than increasing to infinity. From this, an effective gravitational mass could be defined as m effective over m equals 1 plus alpha over r all to the power minus 2. So for large r, Newton's law is obeyed, m effective over m equals 1. But as r goes to 0, m effective also goes to 0. This means that the attractive force between two masses does not increase to infinity as masses approach each other. Qualitatively, the time curvature produces an ever-increasing attractive force, but as spatial curvature becomes important at small r, this produces repulsion. There is therefore no singularity at the origin of coordinates where the laws of physics would break down. Furthermore, we may write the proper velocity of free fall as r dot squared over c squared equals 1 minus a, which gives r dot equals c times the square root of alpha over r plus alpha in equation 11. This means that for r to 0, we have r dot goes to c, the speed of light. On the other hand, Hilbert's solution predicts that r dot goes to c for r goes to alpha, and r dot goes to infinity for r goes to 0. The small difference between r bar and r clearly becomes crucially significant the smaller r becomes. For a mass the magnitude of the Sun, for example, alpha equals 2gm over c squared is just less than just 3 kilometers. The fact that the relationship between r bar and r is linear means that differentials dr and dr bar are equal, and this helps to simplify much of the mathematics. So, to summarize, I have postulated here that Newton's law of gravitation relates solely to the contribution to gravity made by time curvature, space being Euclidean and not curved. This suggests that the currently accepted black hole solution is non-physical. Replacing it with a regular solution, as I have done here, satisfies Einstein's field equations for the vacuum and agrees with all the usual predictions of GR, such as the bending of starlight and the perihelion rotation of Mercury, but not the prediction relating to black holes. The solution presented here shows that not only is there no horizon in space-time, but since gravitational attraction does not diverge to infinity as masses approach each other, there is also no point singularity at the origin of coordinates where physics would break down.